our section or our unit that we're starting now is on basically Taylor polynomials and things called Taylor series. Maclaurin polynomials, which is what you see written here, is just a specific type of Taylor polynomial, and I'll explain what it is that's specific about it very soon. If you think about it, the types of functions you've been most used to dealing with back since as early as pre-algebra are polynomials. And the purpose of Taylor polynomials is to use polynomials, which we're more familiar with, and that's just to make sure you know what I'm talking about, x squared, x cubed, x to the fourth, to use other functions, to write other functions in terms of polynomials. Now I realize how strange that might sound. How can we write e to the x as a polynomial? Or how can we write sine of x as a polynomial? Well, there actually is a way, and we're going to look at that today. So let's start by looking at e to the x. And let's just pull this up in the calculator, in fact. So I'm just going to plug in e to the x. And actually, I think I'm zoomed out a little bit, so let me put back a normal zoom. Okay, sorry about the jump there. The calculator program died on me, but it's back now. So that's e to the x. So if you think about it, if we're trying to use some other function to approximate another function, we would at least like them to work in one point. So Maclaurin always chooses 0. That's actually what is specific about Maclaurin. It always does what they call centers itself at 0. So we want at least one point to be right. So let's consider f of x equals e to the x. And if we want it to be correct at 0, then we're saying, okay, f of 0 has to equal 1, because that would be e to the 0 equals 1. Okay, so we want to pass through the point 1. Well, the simplest way to do that is to just use y equals 1. Okay, so if I now plot y equals 1, well, how similar are those? Not very similar. But at 0, they're exactly the same. But as you can see by the graph, pretty much anywhere else they're not very close to each other. So that's not going to be enough. So maybe more than just wanting to have a similar point, we would like to have a similar slope, for example. Okay, well, we know from calculus we can find slope using the derivative. So let's take the derivative of this function. We'll do f prime of x. So the derivative of e to the x is just itself. And we want to know the slope at 0. So if we plug in 0, we get 1 again. Okay, so think about something that has a slope of 1 and passes through the point 0, 1. Okay, so that's going to be x plus 1. Has a slope of 1 and it passes through the point 0, 1. So let's graph that and see how that looks. So instead of just y equals 1, we'll try y equals x plus 1. Alright, still frankly not very good, but I think you can agree with me it's better than the horizontal line was. Also, this is particularly going to be better anywhere close to 0. So this still may only be exact at 0, but I think you could agree with me right around 0, it's a decent estimate. Now the farther away we get from 0, the worse it is, but it's getting better. Okay, so if you think about what we've done so far, we've made sure the original function was the same at 0. That is, we made sure it equaled 1. We made sure that the derivative, or the slope, was the same at 0. Again, for this equation it was 1. So we would want to keep going with this pattern and say, okay, well maybe we want the concavity to match. Well, that would mean we want the second derivatives to match. And so e to the x, if you plug in 0 in the second derivative, you again just get 1. Now, I'm not going to explain in this video exactly how you derive this, but if you use these 3 pieces of information and then try to write a function, you'll get y equals 1/2 x squared plus x plus 1. So let's graph that one and see what it looks like. So 1/2 x squared plus x plus 1. Alright, I think you can agree with me that at least on the right side of the graph, we're getting better. It is more similar to e to the x than it was before, so it's getting better. Now I'm going to do a couple things here to show you how we can keep improving this. First, if you notice, we actually keep adding a term on the front end, and that means having to retype everything in our calculator or insert. So let's just reverse the order of these things. So this would just be 1 plus x, and this would be 1 plus x plus 1 half x squared. So without going into a lot of explanation of why, the next term we would add to make it more accurate, and this would come from making sure that the third derivative matched up. We would get plus 1/6 x cubed. So again, I'm going to rewrite this so I've got, I'm going in the other order, so I can just add the extra term on the end. So 1 plus x plus 1 half x squared plus 1 over 6 x cubed. Let's check this out now. Okay. Again, not so good on the left side, but on the right side, it's getting even better. I mean, that's a lot closer than it was before. So let's just add one more term just to show you what we've got. We would add the term 1/24 x to the 4th. Plus 1 over 24 times x to the 4th. Now let's check out this graph. So the first one it draws is e to the x. That's what we're trying to approximate. I think you can see that is getting better and better and better. So the more terms we have, the better we seem to be. So you can probably already guess where we're headed with this. If we can somehow turn this into an infinite series where the number of terms just keeps going and going, we can make this identical to e to the x. So I want to look and see if you see the pattern for what's happening with e to the x here, because this works for e to the x. If you notice, we start with 1, and then we added x, then we added 1 half x squared. And now let's look carefully at these coefficients. We started with just 1, and then 1 again, and then 1 half, and then 1/6, and then 1/24. Well, what's actually happening if you just focus on the denominators is they're going by factorials. So this is really 1 over 2 factorial, and then 1 over 3 factorial, and then 1 over 4 factorial. So the pattern with e to the x is 1 over n factorial times x to the n. So if you want to approximate e to the x, you can use this formula. Now again, the more terms you use, the more accurate it will be. For now, we're just dealing with the finite, so we're gonna jump into series later on. For now, when they talk about Taylor polynomials, they really are just talking about a finite amount. It could be 1 term, 2 terms, 3 terms, 4 terms, 5 terms, 100 terms, but it's going to be a finite amount. Okay, now you may be thinking, well, I have no idea how you got that equation in the first place, and it seems like it would take a whole lot of work to do this for every single function there is. And you're right. Fortunately, there's actually a pattern for all of them. Now, they're all not quite as simple as e to the x, but there is a pattern we can follow to find the Taylor polynomial for any function there is. So that's where this comes in. Again, we're focusing on the Maclaurin polynomial right now. That's just a Taylor polynomial that's centered at 0. We'll talk later about what happens if we're centered somewhere else. And just to kind of explain again what centered means, we want to at least have one point where we're exactly right. So in this case, we're choosing 0 as that point. We're going to say, okay, we're going to firmly fix that we're going to be correct and right on target at 0, and then the farther away we get from 0, the less accurate we're going to be, but anything at 0 or around 0, we should be pretty good. So it's written like this: p sub n of x equals f of 0 plus f prime of 0x plus f double prime of x over 2 factorial x squared, and so on. I'm sure you can read, so I'm not going to just keep saying it out loud. I know that's hard to understand sometimes. Now this may look extremely complicated. But I want you to notice something. The only things that you are actually going to have to be plugging in are these. Actually, there's a typo right there. That should be a 0. My mistake. Everything else is just a factorial. I mean, that's not a big deal. Just a number factorial. Your calculator does that for you. And the other is just x with a power. Also not a big deal. So the only thing you really have to do to create these is plug numbers into the original equation and into its derivatives. So if you can take derivatives and plug in a number, in this case 0, you can do these. Now you do need to have this formula memorized. You need to be able to apply this to anything I give you. So I won't necessarily ever say, please write the general form for the Maclaurin polynomial or Taylor polynomial, but you do need to know it well enough that you can follow this pattern and use it every time. Just for the sake of time, I'm going to stop this video right here. If you just go to the next video, part 2, it will show you some examples of how we can do this with other functions.